Hello everyone, it's December the 8th, but we're doing for December the 9th because it's late at night. Alright, so before we start today, I'd like to go back to yesterday's problem. So yesterday we were handling designing Twitter, and we solved it. We solved it nicely using merging k sorted lists and using heap and whatnot. And then I read the discussions, and the majority of the solutions are the same, right? And this is from Mr. Pachman, and he solved it the same idea. It's the exact same idea, but the solution he provided is just the next level. Like if you, I mean, I haven't read. I should have read more Python code, but I haven't read enough Python code to really know if this is considered like really brilliant. But to me, this piece of code is beyond my wildest imagination. Like the amount, like this comment best summarizes, right? The insights, the level of insights into Python itself is beyond my wildest imagination. All right, so we can actually delve into it a little bit. I mean, this is fine. Followers, right? A follow is it's a set in a default dictionary. We use that as well, and this is a deck, which is also fine, and it's not too out of the blue. But what is out of the blue to begin with is this thing, itertools.count. I go, what the hell is itertool.count? This is basically an infinite array, but lazily implemented. So we all know itertools is Python's implementation of a lot of functional programming paradigms, and count is one of them. Because in functional programming, you can implement a lazy list. I was thinking about in Scala, you can implement a lazy list, which means there is no end condition in this list. The list can produce forever, but it does not produce right now. It produces every time you call it. So that's why you do this. Basically, you're saying this timer is going to be following a counter, and the step is -1. And remember, we need to create a heap. Python is min heap, so we need the time to tick backwards, right? And to get the next count, we just call it next. So that's like in my solution, I set up a separate value, a variable, self dot time ticking, and that's the one I created. And every time I just minus equal 1, which is fine, right? It's fine. But this is it's just neat, right? It's very, very neat because Python has a tool to do that specifically in its built-in library, .count. All right, that's the first part. And post tweet, I mean, there's nothing really too special about this, right? And I mean, the good part is it's append left, so it might be easier to work that way. So because of this, we're using append left. So when we do the merging, we can go from the front to the end. So that's why it's using a deck. That's fine. But the real gem is here. So first of all, we see a heap q.merge. So like, wait, what the heck is a heap q.merge? And then you see him taken. So this is taking all the user ID plus myself, right? And then for each user ID, I'm gonna get the tweets. So get all the tweets, and then I'll deconstruct it, just spread it out, and passing it into heap q.merge. So the first question in my head is, hold a second. When you do this, aren't you grabbing all the tweets? Right? Like if we have millions of tweets, I'm grabbing all of them. Am I doing the merge, heap q.merge for all of them? Well, I read the documentation. What heap q.merge does is merge k sorted list. That's exactly what this does. So the argument passed to heap q.merge required to be a bunch of sorted lists. And all of these tweets are sorted lists, sorted by the timer, right? So all of these are sorted lists, and then we pass into it, and then the heap cube module will do the merge for us. But the most important part is it does not do the merge right now, right? It does not do the merge for everything. No, this one simply creates an iterator, right? It's an iterator. So tweets just returns immediately, and it will produce one item at a time when you call next, right? So tweets is an iterator. It's not a list. So this is completely fine. It's lazily evaluated. And then the last piece is itertools.islice. So this is itertools version of doing the slicing. Now we know how to do slicing in Python with the brackets, but this is the itertools version, and it's lazily evaluated. So this one, islice, tweets this thing. Remember, this is an iterator, and I'm gonna get first 10, right? Slice 10. So this one will run 10 times. This will not run, right? At this point, it does not run because it's lazily evaluated. And in here, it will run 10 times. And each time it runs, it basically call the heap queue, and then we just popping things out. So that's it, right? 2 lines. Remember how long I have to write it? That is 2 lines. And of course, there are even, I think this one is even better. Use the heap queue itself to call n smallest. It's the same thing, but it doesn't matter. This is just a little bit niceties here. But the overall idea of using itertools.count, using heapqueue.merge, these are just the insights into Python's language. It's beyond my imagination. I highly doubt that I will ever be able to write code like this. This is so good, right? This is so good. You look at it, it's like, oh my god, this is a piece of art. But we try to emulate it. I mean, it's hard to. I mean, we have different intellectual levels, right? But you learn and you just try. Like now I know count, so in the future, if I need a counter, I will not do a counter myself. I will just use itertools.count, right? And if I need to do merge, well, the amount of I don't think there are that many occasions that I need to do heap2.merge. So I don't know if I'll ever use this, but this is such a good thing to know here, right? And of course, what I want, right? What I really want, itertools and collections are 2 fantastic built-in packages, built-in modules. I want to see if there are any good tutorials, right, to go through every single thing in itertools, explain them, and has good applications out of it, so I can really dial into it. I mean, lazy evaluation is just as good. It saves memory and gets you closer to functional programming. Functional programming is nice, right? But anyway, so this is just some insight I like to share. I read this yesterday and I was like, oh my god, this is so good. All right, so that's that. So close this, and I just close it. Jeez, getting it today. So today we have jump game 3, which I just checked. I've done this before. Jump game 3, and I did pretty well. I think it's a year ago, November. I had 2 attempts, and both worked. So I don't expect this to be too difficult, but who knows? The fact that I'm doing at night usually is it's not a good indication. Right? Things will go very well. Things will be bumpy, but it's fine. Right? We adapt into this new style. Doing at night, because usually my efficiency drops at night, like let's say past 7 or 8 o'clock. I work, like I kept working, but the efficiency is dropped. So might as well do these things at the end of the day. Yeah, if you check this, you can see the last time I did it was last year, right? November 29th. I did 2 times and both passed. So I don't expect this to be too hard. Okay, array, non-negative integers initially pointed at start. Oh, at start as an index. When you are at index I, you can jump to I plus array I or I minus array. I check if you can reach to any index with value 0. Or if you reach the index with value 0, you're going to stay there. You cannot jump outside of the array at any time. Okay, so at 5, 0, 1, 2, 3, 4, 5, at 1, so I can jump. All possible to reach at index 3 are index 5, jump to 4, 4 jump to 1, 1 will jump to 5, I can jump to 6, and then jump to 4, and 1, 3. Yeah. So again, this is already give you a hint. Once you jump to 4, you can go to 3, right? You can go to 3. So that is the hint. We start at 0, right? When I jump, the 0 we only have one way to go. 0 is to 4, 4 to here, and this to this. Yeah. If I start at 2, 0, 1, 2, there's no way. Well, I can jump here. This one will just jumping back and forth. I can jump here. This one will jump 1, 2, 3 to here, and then I got inside loop, so I cannot. Okay. So we know the mechanics. I think this is DP in my mind right now. So basically, if we know if any position can jump to 0, all right? So I just say which one can jump to 0. Well, the one, so 0, so we need to find where 0 is, right? So this one is 0, 1, 2, 3. 0 is 3, right? So we need a position, right, that, so the place that can jump to, so like F here, right, that's 4, so that should be 1, and this should be 1. So if we have a 1, then from this position we can jump, right? And then 1, 2, 3, 1, 2, 3. So once you write it out, if this is the start, and then we go, this would be 1, 2, 3. 1, 2, 3. So by this, we know this is the only position, right? This is the only position that can jump to 0, okay? Then from this position, we find the next position. Basically, now the question turns into, can we start from 5 to jump to this position, right? And the answer is, from this position, we do the same thing, right? So we say we're gonna go 1, right? 2, 3, 4, 5. So this one we find we can go to here, right? This one can jump. That's 4, right? And then from this position, I can go from this position. Yeah, so that's it. So how do we summarize this? Now to summarize this, that's one way to go. I see the other way. The other way is just start from 5, and we just treat it as a binary tree. You have 2 ways to go, right? And we can cache. Maybe that one is an easier way. Oh, those 2 solutions. Maybe one is BFS, the other DFS. Okay, so from here, I say I'm gonna go 2 ways, right? And then we end in here, and the other one end in here. And then from this, so from each one, if I've visited before, but I have not visited before, Okay, so that can work. Yeah, because we just jump, and this one would jump, but this one I already visited. So everyone will visit only once, right? And then once it reaches, then it's true. If it does not reach, then it's false. How does the cache work? Or maybe there's a better ways to handle this. How about this? Right? 0, 1, 2. So this one I start going here, I start going here, right? Or the path. If the path goes back onto itself, then that's it. So one path will only lead down to, yeah, if we can go to 0, then we will not revisit any, like this path should be unique, right? We will not go back onto itself, because if I go back onto itself, and then we're just repeating, so the path shall be unique. So from the start position, I can go. Actually, every time I go, I can just set this value to -1, right? And then every next step, we're going to check. If it's -1, that means we're going to go back. Then we don't go it, and then we try the other route. And if neither route gives us a result, then we return false. So in this case, 2, I can go here. I can go here. If I go here, 3, I go here. And then from this, I either go this, and boom, this one I revisit, I can now go. So this one can only go here. And when I go here, this one can only go here. Boom, that's also no go. So this one's false, right? So all the way false. And now I start from the other branch. It will go here, and then it's already visited. So that is also a false. Ooh, visited. So we need to maintain two things. We need to maintain a cache, right? And then also a path. But the path is going to be backtracking. So it's backtracking as we go on the path, and we're going to cache it. Okay. I don't think I will do two solutions for this one, because I think no, I've done this already. I think it's enough to just do the DFS. Okay. Can reach. All right. Have an array, have a start, def DFS. We're gonna have the current index, right? Current index, and we need the path. We don't need a path. Array can be a path, and that's it. This one gonna return a Boolean value, right? Boolean value. All right. So what do we do? So we're gonna say index, right? So add an index. And let's cache this as well. So we say from func tools import ALRU cache. Okay. ALRU cache max size equals none. I spelled it wrong. Max size. Okay. Given the current index, right? I have the current index, so I visited. We need to attempt equals array index, and then I visited. We say array index is going to be -1, right? And then I'm going to say is I'm going to visit two branches. right? 2 branches. How do we visit the 2 branch? So it's index plus temp, right? We say if index plus temp is smaller than n, and array index plus temp is larger or equal to 0. Then we can call DFS, right, index plus temp, we just visit that one, and we say if this and this and this is true, now we return true. Right, otherwise, we visit the other side, say index minus, right? If the minus is going to be larger or equal to 0, and index this is larger or equal to 0, and this with DFS this. If it's true, then we can true. Otherwise, when it turn it back, equals temp, and then return false, right? And then eventually, when I return DFS start. So this guarantees, because we're running ON, every single node will be visited once. Okay. So first test case. This one is true, right? Second test case. This one is true as well. And third test case is false. Okay, this one is false. Okay, so let's see, we have array and start. And this is can reach array and start. I'll try it. Oh, that is bad. That is bad, bad, bad. What the hell? Alright, I have issues. Oof. Okay, oh, what went wrong? That's alright. It's alright. You know, we just print index, right, and array. And let's just see. So we start at 5. Okay, probably we should do this after we do this. All right, so at 5 we set this to -1. And then we go plus. So we go here. Okay, and this one can only go to this. And this can only go this. All right. Oh, I did not. My bad. So if array index is equal to 0, return true. I do not have any condition to return true, so that is why it's not working. All right. So this one shall be right. There we go. Okay. All right. I'm just gonna go. Oh, a terrible, terrible runtime compared to previous. What the hell? Like twice as slow with a lot more memory usage. Okay. Is it because they have more test cases? If there's more test cases, then that's fine. But if it's not, then there's something seriously wrong. What would be wrong? Huh? I don't know. Yeah, it's terrible. 56 test cases. 54. Okay. So we do have a little bit more test cases. So that's why. And this one still, we're expecting to be around 300, right? So we write it down first, and then I want to check what my previous solution is. Okay, so this is this 3 DFS with backtracking, right? With backtracking and caching. I think it's ON, every single no visit once, because I will not visit them twice. Yeah, it's ON, and maybe it's because I don't think so. We visit every single one, and then if we find a loop, that will return false. Yeah, I think that's fine. How long? 452. That is very, very long. Only 13%. All right, let's see what solution I had in the past. This is today. This is in the past. Okay. DFS. Oh, yeah, that's what I did. So DFS and is seen. If not seen, and index is in this, if this return true, otherwise seen, and then return DFS left or DFS right. Yeah, I think that's exactly the same as I had here, just with a slightly different implementation. I actually do like this one better, huh? Yeah, we call it first, and then we check this. I think this is how I like to do it. I check it first. I make sure we can go, then I go. I see. So basically what I'm saying is if this, we put this one on top. So if 0 smaller equal to index smaller than n, and array index is larger equal to 0, then we say if this is return true. Otherwise, we set this, and we can return directly DFS index plus temp. Oh, how do we backtrack? We cannot return, because if we return, its index is forever changed. So we should res equals this, or DFS index minus 10, right? And then index equals temp, and return res, right? So that's this, all this, and if not, return this. Yeah, so this is, I think it's a slightly more elegant solution. Do you think this is faster? I don't know. So update. I checked my solution a year ago and updated the current solution. So the main difference, is that the checking for the validity of an index happens when DFS is called on this index. Previously, we made the check before calling DFS. Let's see if this one will make it faster. Might as well. But if it does, then I cannot understand why this will make things faster. I don't think we'll make it any like significantly faster. Yeah, just regularly faster. So with this update, we hit 341 milliseconds with a 28%. So that's more normal. That's more normal. I think the reason is the logic is just easier, right? The logic is easier. We don't have like if, gigantic, else, and stuff. And this one is straightforward. Okay, straightforward. But anyway, this one is done. I don't have to read. Okay, I'm going to do the next one. Right into it. Count numbers with unique digits. Given an integer, return the count of all numbers with unique digits x where total numbers in the range of 0 to 100, so smaller than that, including 1122, 33. Okay. Count. Wait, hold on. Return the count of all numbers with unique digits. Oh, excluding. Okay, unique digits, which means they cannot be duplicates. So one duplicate, two duplicates, they cannot be. This is actually an interesting question. I can see this one be Project Euler. Return the count of all numbers with unique digits. Okay, so if n is equal to 1, so we're talking about 0 to 9, that is 9, all of them. If n equal to 2, then we're talking about unique digits is 1122, right, all the way to 99. So that's 100 minus 9, so that's 91. How about n equal to 3? So n equal to 3, we have 91 of the first two, so we just need to handle from 100 all the way to 999. So how many of them are unique? Well, we know how many of them have duplicates, right? So, because we have 3 digits and any 2 pairs within a digit, right? So I have 3 digits, let's call them position A1, A2, and A3. So we can have A1, A2 is duplicate, A1, A3 is duplicate, and A2, A3 are duplicates, right? So we're going to consider all the values that we have duplicates. So let's say the duplicate is going to be, say, 1, 1, right? So if 1, 1 at the first 2 position, then we have the last one, 0 to 9, so that's a 10. And then 1, 1 on the A1, A3, so that's a 10. 1, 1 at the A1, A2, and A3, that's 10. So that's 30 values. And now we also count 1, 1, 1 multiple times, right? We count 1, 1, 1 on 3 different occasions. So we need to do 30 minus 2. So that gives us, oh shoot, and the leading cannot be 0. Leading cannot be 0. Oh, so okay. So 1, 1 something will give us, yeah, we count all of them. 1, 1 something will give us 0 to 9. That gives us 10. 1 something 1 will give us 10. Right? Something 1, 1 will give us 9 because the first value cannot be 0. So it's 1 to 9. So that altogether is 29. And then 1, 1, 1 is counted 3 times, so 29 minus 2, so that's 27, right? So the duplicate, including 1, is 27. Now including 2 is also 27, 3, 27. So 1 to 9 is 9. Everything shall have 27. Well, the last part is a 0, 0. So we cannot do 0, 0 something. We cannot do 0 something 0. We can only doing something 0, 0. So basically just 1, 0, 0, 2, 0, 0, all the way to 9, 0, 0. So that's plus 9. Right? So I can actually compute. So the total number is going to be 27 times 9 plus 9. 252. Right? So this one will give us 100 to 999. How many is that? That's 1,000. That's 900. 900 values, right? So 900 values minus 27 times 9 plus 9. 648 unique values. I'm gonna test this. See if we got it right. Oh, that's 3. 2 is 91. 3 is going to be 648 plus 91 plus 9. 748. Ew. That is not correct. That's not correct. 739. Okay, so we have a little bit issue. All right, it's fine. It's fine. It's fine. Let's try to work it out. All right, 1 1. For one thing, 0 to 9 is 10 values. So first one is actually 10. So now my value is going to be 749. 749, I'm counting 10 more. 10, counting 10 too much, so I'm not counting 10 values. That's interesting. Okay. All right, I'll do it again. So 1 1, 2 2, all the way to 9 9, right? 0 0 is 9. So 1 0 0, 2 0 0, all the way to 9 0 0. That's it. So I have 9 of them. Now we'll go 1 1. We'll go 1 1 something. If it's a 1 1 something, we have 10. Because 1 1 0 all the way to 1 1 9. 1 something 1 is also going to be 10. 1 0 1, 1 1 1, 1 2 1, all the way to 1 9 1. That's 10. Something 1 1. Now 0 cannot take the first spot because we need we need a one, at least one up front, right? So 1 2 3 all the way to 9. So that's 9. Right? So add them together, we have 29. But among the 29, 111 is counted 3 times, right? So we have 111 at first, and then 111 at the second, and then 111 at the third. Everything we have 111. So with a minus 2, that gives us 27. That's why I have 27, right? So 27 for all ones. Oh, I see. 91, I included 10 already. Oh, that's why. So actually it should be 81. Oh, no, that's right. That's right. That's 739. So 10 plus 81, and then plus 649. Boom, 739. Okay. All right, let's try to work out 4. But I'm going to do it slightly differently. So 4, we have 4 positions, right? Actually, maybe we can just do all of them, right? So we say we're in a duplicate. So 4 choose 2. All right, 4 choose 2. So 4 choose 2. We have 6 different possibilities, all right? Oh, then we have more double counting issues. Don't forget, or double counting. Maybe this is not the best way. Hold on, let me think again. If I have two values, right? And at first I say I can take 0 to 9. And once I take 0 to 9, that gives us 10 different, well, I probably don't say 0 to 9, 1 to 9. All right. 1 to 9, that gives us 9 different options. And then, how about the second one? If I take first one as 1, and the second one we have 9 different options. So it's 9 times 9, that equals 81. Okay. How about 3? So 3 is the first can take of 9 different options. And second, right? So the first one is 1, the second cannot take 1, so we have 9 different options. And the third one cannot take, right? So it's 1 to 9. So second can take 0 to 9, except for one of them. That's 9. The third one is 0 to 9, because 997, right? 9. That's only 567. Oh, because I'm missing something. Okay. Hold on. So first is 9, second is 9. The third one, right? The third one, that's interesting. The third one, if I want to, I don't want to match the second one. The second one can take, if the first one is 1, the second one can take 0, 2, 3, all the way to 9. And if the second one is set, right, then the third one can take 0, not these two, all the way to 9. So yeah, that's like 7 different values I can take for the third one. But that's not the answer for all the unique values. Second is going to be 9 different options. That's all unique. And the third, oh, I think third is different. So first is 9, second is 9, third is going to be, because I take 2 values already, right? So I have 10 digits, right? I have, and then minus 2. Shouldn't that be 8? So it's 9 times 9 times 8. Yeah, that's 8. That's 648, right? So 4 digits. First is 9, second is 9, third is 8, that is 7. So it's going to be 9 times 9 times 8 times 7. So this plus this plus this plus this. So 4, I'm expecting 4 to give us 5,275. 5275. Boom. All right. So we have a math solution for this. I see why people don't like it. They're like, I don't know, we're coming here to do programming, right? This is a programming problem. This is to give us math problem. Why? Well, the reason why is not all problems shall be solved using the programming kind of ways of thinking, right? There are different ways to solve problems. Programming is just one tool. If it can solve, if you think about math, is basically just like summarizing a program, which is actually very nice, right? So, oh, we actually do factorial. No, that's actually not factorial. It's just multiply. Ew. How do we do multiply? Reduce. We can reduce. Okay. We don't have reduce, so reduce is inside functools, import reduce, and we can from operators import mul. Wait, is it mul? I mean, wait. Do you want the factorial? I mean, we can do factorial. It's just it's just one factorial divided by the other factorial, and then we can avoid using reduce. Let's write both, just for fun. All right, I forgot operators. Operators Python. Is it mul? It might be mul, but I forgot. If add, it could be multiply. Where are you? Multiply. Yeah, it's mul. It's mul. I see it. Mul AB. Yeah. So go ahead and import mul, and then we're just gonna return, right, 9 times reduce mul. That's the function, and it's gonna be range, right, from 9 to n minus, no, 9 minus n, right? If it's 1, it should be 9 to 9. If it's 2, it should be 9, which means we're gonna go to 8. So it's gonna be this plus 1. Right? If it's 3, 9 minus 3. Wait, hold on. If n is 1, no. I think I don't have to add. It's just, if n is 1, 9 minus 1 is 8, right? So we go range from 9 to 8, right? 9 to 8, and 8 doesn't take, so we can only take 9. Yeah, we should not be able to take 9 if n is 1. If n is 2, yeah, we do have to add 1. So we're gonna, let's see if my understanding of this works. All right, we have a couple of test cases, right? We have 0, which gives 1, which is 0 by itself. 1 shall give us 10, right? 2 give us 91. 3 give us 739. 4 give us 5,275. Let's see, this is n. This is count number n. No module name operators. Operator, no s. Reduce of empty sequence with no initial values. Oh shoot, we need initial values. How do we set initial values? Python reduce, I forgot. And maybe you just pass another value like this. But I want to make sure. This is just the ridiculousness of the search engine of Bing, right? You type Python reduce, I expect the documentation to come up first. That's fine. Reduce, where are you? Function iterable initializer. So do I call initial? I think I just pass in 1. That ain't right. That ain't right. And 2 digits. We got 81. Oh yes, I need to add. Hi, shoot. Okay, I need to add. Screw me. It should not be special case, right? If n is 0. Oh yeah, n is 0 is no starting thing. It's a special case. Okay, that's fine. How do we handle the special case? Well, the special case is just 1, right? Right. I should not have this. It should be like if n so 9 is still not right. So 0 should be 1, right? So we say if n else 1, right? Now the first one passed, and the second now we just need to add them together, right? We just need to sum them together. So we just need to sum this, right, for say I in range n, and this one become I. Nope, that ain't right, because have to be I plus 1. Oh, it's still not right. Let's not sum them together. Why would it be 18? 10 plus. Oh, if n. That's if I. There we go. And now we pass. All right. So let's do this to 10. So we can remove one of this. This is fine. And then for I in range, sum. Okay. And if you can write in one line, why not? We're gonna check one more. Okay. Oh, yeah, just 5, 6, 7, 8. That's okay. 1 and 0. Right. These are all possible test cases. Now this one can be run, can be checked against all the test cases. Yeah, and we pass. So we'll pass. 55. Oh, I know. This is the trick. Mírame. Eso es the trick. I think it's called answer, right? Oh yeah. Esta es la solución. ¿Sí? Poner la solución aquí. Y solo necesito return self.answer n. Así es la vida. Mira. Mucho más rápido. No mucho más. 52 milisegundos. Está bien. Está bien. All right, so what do we learn? Given, right, n-digit number, the first position has 9 choices. The second position also has 9 choices. Well, more explanation. 0 to 9, but we cannot take 0. Right? Second also had 9 choices. We're going to say 0 to 9, but we cannot take the number on the first position. The third position has 8 choices. The fourth has 7, etc. Right. Thus, the number of unique values in n-digit is 9 times 9 times 8 times da, 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 until we cannot time anymore. Until all digits are considered. The special case happens right when n equals 1, which has 10 unique values. No, that's not a special case. Special case is when n equals 0, which has 1 unique value. Pero no es rápido. Pienso que si uso la solución de matemática, es posible, es muy posible que dura mucho rápido, ¿sí? Pero eso no es 16%. All right, let's read the discussion. DPO1. And what's the point of this? Well, the point is the practice of math. Dummy. We're just gonna read it and then see how it goes, and we're gonna call it a day. Yeah, I think 2 questions is a good dose for me right now. It won't take too much time, and it still give me a good dose of practice every day. More than 2, puedo con problemas fáciles pero no medianos. Sí, lo mismo solución. Sí, lo mismo solución. Yeah, it is a 1. Yeah, that's why. How did you get to this list? Oh, you just get to this list. Oh, initially n is 10? I don't know. The question must have changed over the years. I want to see the Python. How did you guys write Python? Maybe I should post this. Just for fun. Esperando, esperando. Cada vez tengo que esperar por mucho tiempo. Def count. 9 times count 9 plus 10. Oh, mira. Look at this. Alright. I'm gonna post this. Just for the lols. That'll be fun. Alright, new. And usual one, I always say Python 3. One-liner. Tag? Do you want to put tags? Is Python a tag? Python is a tag. Is a one-liner a tag? One-liner is a tag. Math must be a tag. Yeah, math is a tag. That's it. Let's include those as well. And the thing is, since I've already written the explanation, there's no need for me to rewrite the explanation. It's right there. And we just post it. Alright, that's it. That's it for today. Voy a verte mañana. Te, no. Voy a ver, no. Oh. Los? Wait, what is the pronoun for this? Ver. I can say a ver vos, right? Vosotros. A ver vosotros. A ver usted.